So we computed various expectation values of e to the power kx and related things in the last class. We now want to use that to understand the string to understand what the string scattering. Okay? So how are we going to do that? Well, let's start with the simplest example. Well, first let me remind you of the formula we use in the beginning. It's that e to the power I k I of yi product over I expectation value is equal to yij product I less than j to alpha prime ki. Here is the right last payment. Okay. Now let's apply this to the study of three tachyons scattering. So the three tachyons scattering according to our general rules has we've got three C operators. So let's say that a C operator at y1, a C operator at y2, and a C operator at y3 times e to the power I k1 at y1, k1 the x at y1, e to the power I k2 dot x at y2, and e to the power I k3 dot x at y3. Okay. Now we want to understand those expectation values. Well, the conformal field theory is split up into a conformal field theory on C's and a conformal field theory of X's. We can do the expectation values separately. And this part we've already seen. It's y12, y23, y13. We've computed. So that's the part, the C's. Now let's compute the thing with the X's. Okay? So the thing with the X's goes as follows. We've got e to the power, so we get y12 to the power equal alpha prime into k1 dot k2, y23 into 2 alpha prime k2 dot k3, and y13 into 2 alpha prime k1. Okay. Now, remember that from general principles, all three vertex operators are fixed at particular points, y1, y2, y3. Right? We could choose these points to be anything, but in this simple calculation, I've not chosen them to be anything particular. Get them to be arbitrary points, and then, it's consistency check on our procedure that this amplitude should not depend on the insertion points from right. So at first it sounds crazy. How can it work? This just depends on the momentum. So then when you think about it, it works. And how? Remember the k1 dot k2 is equal to k1 plus k1. The whole thing squared minus k1 squared minus k2 squared. Now, k1 plus k2, the whole thing squared is the same as k3 squared. So each of these is given by the master value of the master tachyon. Okay? So, the master tachyon is k squared is the tachyon. The master tachyon is minus 1 by that, right? K squared is 1 by that, right? Okay? So this is equal to minus 1 by that. Because we get 1 by alpha prime minus 1 by alpha prime minus 1. Okay? Sorry, and this had a 2. This is correct. The formula was correct with that. The 2. Right? And so we conclude that y12 is raised to the power minus 1. Similarly, y23 is raised to the power minus 1, y21 is raised to the power minus 1, and we can cancel. This is just reduced to 1. Okay. Now, there is an additional point here that in this particular example is more or less trivial. The amount of additional factor of 2, but it's sort of important in more generality, so I'll make it. And that's it. Look, memory has three objects of momentum k1, k2, and k3. And we place them at some points y1, y2, y3. And we said that, well, it doesn't matter what these points y1, y2, y3 are, because we can choose them to be anything by the appropriate Mobius transformation, the appropriate unfixed conformal transformation that leaves the boundary unchanged. But, you see, any variable of the change that acts in a one-to-one fashion on the boundary cannot change the relative ordering of points. Okay? So, given a particular ordering, okay, now the way that we need to do calculations is to regard the worksheet of the open string as its upper half plane. So the upper half plane is conformally related, is conformally transformable into the disk. Okay? And you identify points at infinity, so that this becomes a boundary and using that reference to the disk. So the points that we put, let's say, y1, y2, and y3, instead of having a linear ordering, we should think of these points having a cyclic. Okay? So it's this cyclical ordering of y1, y2, y3 on the boundary of the worksheet that cannot be changed by coordinate transformations. Okay? So, if we want to sum over all particular ways of inserting our vertex operators, we should sum over all cyclical orderings. And then for a given cyclical ordering, we can choose this y1, y3 to be anything we want. Is this clear? This is fine. Coordinate transformations that are unfixed by a gauge-fixing procedure that allow us to take y1, y2, y3 to anything have to be one-to-one transformations and therefore cannot change the relative ordering of points on the boundary. Is this clear? Okay, so that has to be summed over explicitly. Now, since in this particular simple case, the amplitude did not care, it was not a function of k1, k2, k3. I mean, so if 1 will become perhaps 2. We're not doing these calculations at the level that you strike such factors and drop in delta functions and things. So for this particular calculation, we would not care very much. But it will soon become important in various other things. And it will also become important in this calculation when we generalize a calculation in a particular way. So let me immediately tell you about that. Okay? So that generalization goes as follows. So far we've been talking about open strings living on the strip. Okay? With non-bounded relations at both ends of the strip. Okay. Now, once you have boundary conditions, you've got some special boundary points. You might, with various considerations that we dealt with, tell us what the propagation of the theory has been in the past. That we can't change easily. It's very, very tightly. However, you might want to add new boundary degrees of freedom. New degrees of freedom that live just at the boundary of the worksheet. The question of how you can add new boundary degrees of freedom in a way that preserves conformal invariance and all the other good properties of string theory is an intricate and interesting question. And we will not try to give a thorough analysis of that at all. All we're going to do is to make very all we're going to do is to make a very particular choice. Okay? There are other ways to do it, and that gets into more complicated boundary states of string theory at some point in our course of research will encounter this. But at the moment we're going to talk about a very trivial set of boundary degrees of freedom. The boundary degrees of freedom live in a particular vector space that is finite in dimension. Okay? So there's a finite dimensional vector space living in each boundary. Okay? And we work in some basis of this vector space. So there's some inner product of this vector space, inner space. And we work in some basis, some orthogonal basis, in which the basis vectors we call so the basic vectors are, column 1, 0, 0, 0, 0, 0, 1, 0, 0, and so on. Okay. And we will use the Hamiltonian for his boundary degrees of freedom. The evolution operator of the boundary degrees of freedom to be true. Okay? Which means that along any given boundary, the boundary degrees of freedom don't change. Okay? Basically what I'm saying then is that the open strings in the picture come in different flavors. The flavors are labeled by an index, one index I that runs from 1 to n, where n is anything. Okay? One index I that runs from 1 to n on the left boundary, and one index I that runs from 1 to n on the right boundary. Okay? So, now our open strings on the strip, in addition to being labeled by, what we call is the full Hilbert space that we obtain by quantizing these open strings, is specified by a vector in the tensor product of the Hilbert space we had before, namely the oscillators in the 0 Hertz, and this n square dimensional Hilbert space, which tells us about the boundary degrees of freedom on the left and the right. Okay? So you can think of it as some matrix, okay? N cross n matrix times whatever we had before. Okay? You can think of it as n squared different species of open strings. You've got n squared different species of open strings. Okay? The species does not change in evolution. Okay? But can change in interactions. Okay? Each species behaves identical to every other figure. Is this clear? Okay? Now, this, though we may not see it very systematically each day, turns out to be consistent generalization. It's one of a much larger, there's a whole theory one can build up consistent boundary states or boundary interactions one can put to achieve this thing. I won't stop to try to build that. Okay, at this point. We just look at this as one example of something that's more or less trivial, and therefore, when you look at it carefully, more or less clearly consistent as a generalization of the boundary, this Neumann condition we illustrate. Okay. So now the important thing is that states of the open space and hence vertex operators are labeled not just by the vertex operator labelings that we've got before, the by IKX and derivatives and so on, but also by an n cross n matrix. Okay? So vertex operators vertex operator for tachyons, for instance, a fixed tachyon will have a C of y1, a lambda 1 to some n cross n matrix. And an e to the power I k. Okay. Now, remember that our evolution rule was that an index cannot change at all. Okay? So we've got an open string, and its index cannot change along the path string. However, it comes and interacts with two other open strings. So the index along here is conserved. The index along here is conserved. The index along here is conserved. Okay? Now these open strings are replaced by their vertex operators. What does that tell us about any computation involving the insertion of 3 or more vertex operators? It tells us that you have to put, in addition to what you had before, you also have to put in the trace of lambda 1, lambda 2, lambda 3 going in cyclic order. Is this clear? Okay? So, now let's recompute the three tachyons scattering amplitude. Let's recompute the three tachyons scattering amplitude in this enlarged theory where there are these few boundary degrees of freedom. Okay? So let's do that. So we've already seen we get the answer 1 from the matter part. Okay? For any particular, so right. So suppose we had lambda 1, lambda 2 and lambda 3 associated with e to the power I k x1, e to the power I k x2 and e to the power k1, k1x, k2x, k3x. Yeah, these are our three values. Now, we've already seen that irrespective of what ordering we choose, okay, we get 1 from the matter part and matter and those part combined to the ambient. So there are two different cyclical ordering that we've already seen. So 2 and 3, or 1, 3 and 2. So these two different cyclical orderings, they don't give us equal contributions from the lambdas, because one of them gives us trace of lambda 1, lambda 2, lambda 3. And the second one gives us trace of lambda 1, lambda 3, lambda 2. And these are not the same. Okay? So if we wanted to, we could write this as, for instance, trace of the anti-commutator of lambda 1, lambda 2 with lambda 3 times 1. That's our final answer for three tachyons scattering amplitudes. Okay? Where the tachyons are labeled by their n cross n sort of matrix vertex operator plus the momentum. And the amplitude happens to be independent of the momentum. Is this clear? Okay? Good. Now, we're going to do another 3-point function calculation. This time of scattering of two tachyons will gain. Okay? What is the physical interpretation of this calculation? Somebody. If I take two tachyons and scatter with the gauge goes up, what will help me learn? Whether the tachyon is charged, and if so, how it's charged under this gauge. So of course now everything in the theory carries these n cross n indices. The tachyons and the gauge. So it's a natural guess, if you see that it's correct, that the gauge bosons are going to be non-abelian gauge bosons. Okay? And that the tachyons will be non-abelian tachyons. Okay, but let's start seeing. So let's start seeing. So now what we want to do is to compute. Okay. So the three operators that we have, that's called the gauge boson operator number 1. So we have e to the power k1 dot x. And then it's associated with the polarization vector E dot del x. And this guy comes with its matrix thing lambda. Then we have e to the power I k2 dot x. This is associated with nothing else. And e to the power I k3 dot x. Again associated with nothing else. K2 and k3 are the two tachyon vertex operators. Well, of course, that's all. Polarization. Matrix. Lambda to lambda. The derivative along the line. Yes. Okay. So now let's, and of course there's also the C field into these, and once again there will be three fixed values. Okay, now let's compute the scattering amplitude, the expectation that these vertex operators in this. So once again, we're going to have two orders. We'll have the ordering, let's say 1, 2, 3, and the ordering 1, 3, 2. Okay, so let's do the calculation first for the first one. So that's the calculation for 1, 2, 3. Okay, first three for the C field. That's simple as 1, y1, 2, y1, 3, y2, 3. Okay, and that will be common for both orderings, you know, we'll have that outside. Okay, now let's also do the calculation of this lambda. So that's very simple. So the first guy gets, oh yeah, I'll try to do the calculation both orderings simultaneously. These are the both space. The first guy will get a trace of lambda 1, lambda. Well, okay, if we take now, we have to decide which way we're taking our traces. Let's say we take our traces that way. So clockwise. I'm not sure what the usual convention is, but let's say that we will take our traces this way. Then the matrix is 1 that way. Okay, so lambda 1, lambda 2, lambda 3. And this guy, of course, and there will be something multiplying it. This guy will have a trace of lambda 1, lambda 3, lambda 2. Now then we have to figure out what multiplies it in each of these cases, and what multiplies it in each of these cases comes from the max. So let's work that out. Alright. So, good. So, let's work out what we get by contracting this guy, and this guy, and this guy. In order to do that, we need the rule that we developed last class. The rule that we developed last class helped us to deal with insertions of this del x. So the rule said contract the exponentials as the del x was there and add an additional factor for del x. Okay? So first let's do the contraction of the del x, the exponentials as the del x there, and then divide with the additional factor. So let's look at the term that's y1. So we have y12 to the power of what? Well, it's 2 alpha prime k1 dot k2. Now once again, k1 dot k2, 2k1 dot k2 is k3 squared minus k1 squared minus k2 squared. But k1 squared is 0 and k3 squared is equal to k2 squared. Okay? So we get 0. There is a 2k1 dot k2, which is k3 squared minus k1 squared minus k2 squared. k1 squared is 0, k2 squared is equal to 0. We can see. Okay? Similarly, we get y13 to the power. But y23 is different. For y23, we get 2 k1 squared. So we get k1 squared minus k2 squared minus k3 squared. k1 squared is 0, but k2 squared, k3 squared are each 1 by alpha. Okay? So this becomes minus. Now, it's 2 alpha prime k1 dot k2, but we will give the formula for 2 k1 dot k2. Okay? Yeah, for the same reason that earlier it was minus 1, this is now it's double that. Okay, good. Now what remains is what we get from the insertions. Okay, so what are we going to get from the insertions? So from the insertion we get if you remember what the formula is, it says you get 1 over, there's a number which we will keep track of, overall number. So we have 1 over y1 minus y2 into k2 plus 1 over y1 minus y3, okay, into k3. The general formula was the check where this guy is inserted. This guy is inserted at the point 1. Okay, so you take yi minus yj for all other expressions and have the k of the other guy on top. Okay, and then that guy is going to be dotted with the polarization tensor. That guy is going to be dotted with the polarization tensor that appears up here. In this case, can be vector indices. Okay. Now we come to something important. Now let's process this formula. This formula here has what? It has we have k2 into. Okay. So, the first important point to note is that k3 k1 dot epsilon is 0. K1 dot epsilon is 0. That was one of the physical state conditions. The BRST closed conditions of a vertex operator. Therefore, by numerical conservation, k2 dot epsilon is minus of k3 dot epsilon. Because k1 plus k2 plus k3 is equal to 0. Is this clear? Okay? Good. So what we can get from here? Each of these, this k2 can be replaced by k2 minus k3 by 2. K3 can be replaced by k3 minus k3 by 2. So this is equal to epsilon dot k23, okay, by 2 into 1 by y1 2 plus 1 by y1. Is that right? Oh, sorry, with a minus. Okay, which is epsilon dot k23 by 2 into, now we get y23 over y12 y1. It's y2 minus y3. Y12 is y1 minus 2. Okay? And, okay, so now it all works. You see, the first thing you have to check once again is that everything can be independent of the insertion points. Okay? So that part is going to work. That part is going to work because, well, that part is going to work because now we've got this times y23, so 1 by y23 whole thing squared. So that becomes y13, y13, y23, and that cancels the insertion from the sequences. Okay, and then we have to worry about what we get from the other one. by 2. So, our final answer is epsilon dot 823 into trace of lambda 1 into lambda 2 commutator lambda 3 up to also the sign. Okay? It's a little subtle if you think about it. So I would like each of you to go home and think this minus sign through carefully in your head. Okay? But the net result is that these two orders contribute to the relative minus. Okay? That's the thing that's really important. That's what makes this commutator rather than the anti-commutator we have. In particular, suppose there had been no polarization tensors. Suppose these lambdas are trivial. Okay, where is the minus side by the way? From K32 is minus K23. Okay, so suppose these lambdas have been trivial, this would have just been 0. So it would have been the statement that the tachyon is uncharged under the gauge boson. Okay, well, in the general case it's not trivial. But we also see how this thing, you see, this is the polarization, the matrix structure of the two categories. It's a commutator that appears. Okay? The commutator that appears multiplied by the matrix of the gauge boson. Now this is in fact a statement that the tachyon is interacting with the gauge boson exactly like a minimally coupled adjoint scalar interacts with it. Why is that? Okay, let's write down the Lagrangian for a minimally coupled adjoint. The Lagrangian for a minimally coupled adjoint scalar is trace of del mu phi and d mu phi and d mu phi. So where do we get the two tachyons and one gauge boson interaction from? It comes from one of these d mu's having the AB. And the term of that is A mu commutator phi times phi trace. And this one has the alternative. Okay? You see that this is exactly the same as this lambda term. You know, where we put the commutator doesn't matter under the trace. You can put the commutator for any two of these. It's the same matrix. Whether we call it 1 and 2 or just actually put two scientific orbits with a relative minus sign. That's the invariance. Okay? So this is exactly this color structure. This derivative here is the fact that the amplitude has a K. Okay? And the fact that this derivative contracts with the AU is the fact that the K contracts with the polarization. So we go a little more detail than we have here. You'd say that the final rule for sketching amplitude that follows from this interaction matrix is precisely this, some factor. Okay? So we concluded that the open string theory, I mean, it's really seem very much like open string theory has non-abelian gauge bosons in it. And that the tachyon field is charged like an adjoint scalar under these non-abelian. Now, though we've worked it out specifically for the tachyon, okay, every field in the problem, apart from the gauge boson itself, but every field in the problem enters as an n cross n matrix. Okay? So it's plausible that every field in the problem is charged in the adjoint of this gauge group. Okay? So what I'm saying is that if you work out the first excited state, for instance, 2 copies of that scattering against the tachyon. Once again, you'll find a similar stuff, which will tell you that basically all states of the theory are charged in the adjoint of this UN gauge group. Okay. The one feature that's special in this regard is the gauge boson itself. It's special because it should give you all the interactions. I mean, if our interpretation is correct, it should give you the scattering amplitudes that follow from the interactions of gauge boson with itself in the Yang system. Okay. So now I'm going to read. So something that's interesting to do is to calculate the 3-point scattering of 3 gauge bosons. Okay. I'm going to read that as the exercise. Okay. It's more of a study. You just have to do all this stuff again and again. There's one new element is that in the rule for contraction of these derivatives, you remember there were also these oscillators, effective oscillators in contract. If you just have one derivative, no, there's nothing for it to contract again, so we didn't have to use that. So now we have 3 derivatives. Okay, so there will be oscillator contractions pairwise, in addition to taking the term that is just this piece for all 3 derivatives. Okay? So the structure of the amplitude should be clear. There will be one term when you take this piece for all 3 derivatives, which will be cubic in momentum. And then there will be 3 other terms, which will be linear in momentum. Where you take this term for one of the 2 derivatives and the oscillators for the other. Is that clear? Do you know what I'm talking about? You know what I mean when I say the oscillators? You remember what our rule was for contracting these dead ends? There's a part that contracts as if the exponentials weren't there. That's what we call the oscillators. It can contract therefore only against other dead ends. And there's a part that has background value that we will keep in track of. The background value is a linear momentum. Okay? So the term where you keep all 3 background values will be cubic in momentum. And the term where you keep one momentum to prove the Alexa contracting will be linear. There will be 4 terms. And because of the oscillators, you can choose, there are 3 ways of choosing which phase to contract. Okay, so there will be 4 terms you have to keep track of. I'll just quote you the result from which is. It's a little complicated. Okay, apart from these various delta functions and so on, you get E1 dot E23 into E2 dot E3 plus sign. Okay, and then there's a special term which is plus alpha prime by 2 E1 dot K23 into E2 dot K31 into E3 dot K1. And everything is multiplied by trace of lambda 1 to lambda 2. Okay, now let's interpret these things. First, we look at the trace structure. The trace structure tells us that if there were no matrices because it's combinated, we were just in U1 theory, we get 0. Which is great because gauge bosons don't interact with themselves in the U1. Okay? Now, however, in UN theory they do interact with each other. In the UN theory, they do interact with each other. And these 3 terms are simply the final rules that come out of the usual trace exponent. The usual trace exponent. The 3-point final rules that come out of the usual trace exponent. This term is genuinely different. It's different, for instance, starting from the fact that it is 3 derivatives rather than 1 derivative. And It's different also that it has an extra alpha prime. And it reflects the fact that string theory is not gauge theory. String theory, for the massless degrees of freedom, reduces to gauge theory at very low energies, but has additional interactions that are not that of the minimally coupled gauge theory. So this term, look it up, is reproduced from a term of Lagrangian which is proportional to alpha prime into F mu alpha F alpha. So we'll keep the linear pieces from two of these F's, and we'll keep the linear pieces from all three F's. Yeah, just get the linear pieces from all three F's, and that will give us basically this. Why is that? Why is that? Let's see. So this is okay, let's look out. This is effectively del mu a mu minus del mu a mu. And similarly, del alpha del mu a alpha minus del alpha a. Right. Okay, so three such terms. And why do we get this structure of contraction? Let's see. Yeah, so oh, you're worrying about this one here. There's all these momentum. Okay, I have to say I haven't checked this. I'm just quoting this for Koczynski.
This alpha prime is a term which should not come into
no, the alpha prime is a term that could come. That could come. But doesn't here because we see that. We see that there. And you say that this thing would just be non-zero. Yeah, you're probably right. Oh wait, I'm sorry. I haven't checked this. You're probably right. Yeah, it's probably right. Go to Koczynski. Okay, let me leave this as an exercise. Construct an effective Lagrangian that reproduces this thing. It's going to come with three F's. It's going to have this contraction. Oh, you're almost certainly right. How are we going to get this structure? How are we going to get the structure unless we have almost unless that's Einstein symmetry? This is oh, you see, I know it. You see this. Yeah, you see, this is suppose we think of it in the U1 theory. That's trace of omega cubed where omega is an antisymmetric. And that's probably just
okay. Actually, here also it would be.
Yeah, so maybe.
No.
And these two terms are probably. What?
No. Okay. I think that's what. I think the committee will say this.
As same as this talking about.
Because of that way.
Exactly.
Because the symmetric part is symmetric in mu mu. And
right.
if you are contracting with S mu mu, only the antisymmetric part is going.
Right. So in particular for the human theory, this would just vanish. So it's consistent with this vanishing, the human theory. Yeah, okay. So Koczynski's claim is that this thing will reproduce, that this term in the, such a term in the effective Lagrangian will reproduce this amplitude. I haven't checked it personally, but okay, something like this will do the job, check it out. Okay, good. how the page goes on. And try to convince yourself that what you get from here is exactly what you expect from the ordinary angle of expansion. And what you get from here is some higher order term in string. By the way, this higher order term is not inconsistent with string theory reproduced in gauge theory and low energies. Because if all derivatives, all landscapes are large compared to alpha prime, this term is much smaller compared to this. Because there's two additional derivatives and one additional power of alpha prime compared to this term. So in the derivative expansion, in the limit where landscapes are large in units of alpha prime, this term is suppressed compared to this term. At least naively. Okay? So, such terms are there, but they matter only for configurations that vary on length scales or on energy scales or on the string scale. If we're varying the length scale is large compared to string scale, where energy is low compared to string scale, that term is negligible compared to the vector. Is this clear? Okay? So the lower energies you get back gauge theory, but of course there are corrections around energies. It's very easy. It's very clear. This is a simple. Is this clear?
We would definitely be worried if this was a field theory.
If this was a field theory, yes, we would be worried if this was a field theory. But we know string theory is fantastic on magnitude. Yes. So you see, this is not the only term. If it was the only term, the Lagrangian would be bad. But this is the effective action that comes from summing over all of string theory. But this is one term in the effective action. The first in the effective action is much larger thing. And there are independent ways of understanding that string theory is very finite. So those issues aren't an issue. Issues are basically the same. When we were studying enclosed string theory, we had the gravity, and then we had higher derivative interactions with that gravity. That would be even worse than the gravity Lagrangian. But the whole theory is finite. You see, it's particular regularization that makes sense, which if you expand it out in the lattice spacing, and increasing effective lattice spacing, which is not right? Increasing higher derivative terms. The whole thing is nicely regulated. Just as an analogy, it's not a very good one for string theory, but anyway, if you took something like e to the power minus base squared and base squared, this is a factor that suppresses high number. But if you expand it out in a power series of A, it will look worse and worse as you went to higher and higher numbers. That's roughly what's going on.
But that would be a very non-local term also.
That would be a very non-local term. Yes, it's certainly not easy to make consistent theories of gravity, especially gravity, by hand, doing something. So string theory manages it in a very beautiful and intricate way without doing something crude like that. But just if you want a rough analogy, this is the analogy. And string theory is non-local at that. So, it's not local, but at least there's no precise sense in which it is. The strings are big objects. Strings case, that's fine. Okay. Also, what you mean by locality in a theory of gravity. Okay. Fine. Good. All the questions, comments? Okay. So, now what we want to do is to move on to a discussion of 4-point amplitudes. Okay? So, we're going to move on to a discussion of what's called the Veneziano amplitude, which is actually the first mathematical formula in string theory that has ever written down. It's written down before string theory, and you get to understand this beautiful formula led in part to the work that is how we're going to be string theory. Okay. So, what we're going to do is to try to understand sketching the formula.
So somehow there should definitely be other directions, even if you constrain oneself to just the terms only involved in it.
Even if one is oneself. Well, there will be correction to all products.
Yeah, but they don't appear in this loop.
They don't appear at 3 points.
At 3 points.
Yeah. We've only calculated the 3-point scattering. And the 3-point scattering amplitude classically is exactly equal to that. There's no further variation. Of course, even the 3-point scattering amplitude
This is the most.
would get correct in quantum mechanics once we take the conclusions.
Yeah, so is this the most general thing that you can write down?
No, it isn't the most general thing. Well, oh, you're asking just, okay, maybe it is the most general thing. Yeah, you see, anything with more F's would necessarily contribute only at, say you have 4 F's, the lead on the contribution will be to the 4. Yes, maybe it is the most basically.
No, I mean, do we get any constraint at all from string theory?
Well, there's coefficients.
Yeah, but okay, that is alpha prime. I mean, if you look at
Some square root 3 times alpha prime. I mean, it's very, yeah, okay. Now, in the superstring, when we do this, the same thing in the superstring, many terms that could appear wrong. Okay? But you can understand a lot of that from constraints coming from superstring, from space time translation. Okay? But certainly, if you're just looking at things without looking carefully at supersymmetry, many terms that could appear. The bosonic string is much less constrained. But of course, you know, string, any string, including the bosonic string, gives you a particular answer. All coefficients are particularly determined, is something particular. So, there's a lot of constraints. This is the answer.
Yeah, but at this order, I can just whatever is the question, I can define it as from field theory point of view. So, I mean, if you give relations between this and other things.
Yes. But you have one freedom to define, and then the next time you make sure complete. Okay, good. Alright, we've got Amod's colloquium coming up. But let's just go on, let's miss the introduction. Okay. Let's quickly move on to the 4-point the 4-point tachyon. Okay. So now the 4-point amplitude, as you remember from our study close strings, is interesting because the first time in a calculation of a scattering amplitude, we have to do an integral. It's not just writing a number, we have to do an integral. Right? Because on the version, because you can fix 3 of the 4 vertex operators, so the fourth one is whatever it is. Okay. So let's set up the calculation for that. Okay. So we've got, let's say, 4 vertex operators with pi k1 dot x, which is lambda 1, with pi k2 dot x, lambda 2, and so on. Lambda 3. Okay. Now, I won't try to keep. I'll take it for granted that from formal reasoning, we can set those 3 points to be wherever we want, and set them to 3 convenient places. Then we set them to y1 equals 0, y2 equals 1, y3 equals 0. Okay? So, what do we get? So, firstly, of course, we have product over this yi from the C's. We have y12, y13, y14, y23, y24, y3. This is what comes out of the C's. Okay. Now, anything that does not involve y4 is just some number. So the terms that involve y4 is that y14, y24, and y34. And then there are some numbers. The numbers are like y1 minus y2 is 1. But anything involving y3 is infinity. We have infinity to the power 2. What is it to the power 3? Okay, so this is also infinity. It's infinity to the power 3. More precisely, it's y3 to the power 3 is the limit of y3 goes to infinity. Okay? Now let's see what we get from the momentum contractions. From the momentum contractions we have e to the pi, k1 dot x, and so on. We call this product of pi and x, right? we've got e to the power 2 alpha prime ki dot kj from the Moivre contract. Now let's see what ki dot kj is. What this ki dot kj is this. Sorry, yij. Okay. So, let's look at those terms that involve y3. All such terms are infinity to the power 2 alpha prime into k3 dot k1 plus k2 plus k4. And because anything that involves y3 is basically y3 to this power. So y3 is much larger than right? So it's infinity to the power this, so that's same thing as infinity to the power 2 alpha prime into minus k3 squared. So minus k3 squared was minus 1 by alpha prime. So that's infinity to the power minus 2. How did that cancel? Can you get that again? The screen line?
Yes.
Alright, make something very stupid. Yeah, very stupid. Wrong. Oh, I'm sorry. The C's. That's what I did wrong, right? With the C's, only 3 lines are fixed. Only those 3 C's are here. So it's y12, y23, y12, y13, y23. That's nothing but the forms. Right? So, here we didn't get these guys. And what we did get was infinities. Sorry. And the guy that is integrated over doesn't have C's. Sorry about that. So this infinity squared cancels as minus infinity squared. Minus. Where are the answers plus 1 minus 1? I'm looking at all of that. Okay, so what's left? So what's left is all the stuff that involves y4. So what do we get? The stuff that involves y4 is Okay, again, once again here there's a y12 that we don't care about. There's a y4 into k1 dot k4 into alpha prime. And a y4 minus 1 into k1 dot k2 dot k4 in alpha. Okay, now very quickly some time analysis. Okay, our usual definitions: S is equal to k1 plus k2 the whole thing squared with a minus sign. And let me differ from Kulczynski to write a non-dimensionalized alpha prime. Okay, alpha prime t is equal to minus k1 plus k3 squared. Alpha prime u is equal to minus k1 plus k4. Okay, now then this object is k1 dot k4 is equal to so 2k1 dot k4 with an alpha prime is equal to alpha prime with k1 plus k4 the whole thing squared minus k1 squared minus k4 squared. Alpha prime is equal to minus u minus 2. Okay, so that object there is, so our answer involves the piece dy for y4 to the power minus u minus 2, y4 minus 1 to the power, and then this will be similar except we have x, so minus s. Okay, so that's the kind of integral we have to do. That's the kind of integral we have to do if we want to solve this problem. Okay, now one last thing, and we stop at what I wanted. This y4 is integrated over what range? It's integrated over minus infinity. But you see, the three ranges. What's really important is for we have y1, y2, y3 inserted as 0, 1, infinity in this order. And the integral here from, in this range, from 0 to 1, will give us the same answer as the integral here from 1 to infinity, just because we couldn't parameterize this as 0 and this. See, the only invariant thing is what order the various vertex operators are inserted. Okay? So instead of regarding this integral as going from minus infinity to infinity, we can think of it as three different integrals, one from each of the ranges, minus infinity to 0, 0 to 1, and 1 to infinity. And the part that is from minus infinity to 0 will give us the same answer as 1 to 0 to 1, provided we interchange the vertex operators appropriately. Is this clear? So, actually there are 6 different contributions, each of which is proportional to a very similar integral with some interchangeable vertex operators. You see, what we've got is, so the 6 different contributions are the following. y4 here, or y1, y2, y3, and y4 here, or y1, y2, y3, and y4 here. That's 3, but y1, y2, y3 we chose the particular cyclic order. We could have had y1, y3, y2, and y4, y1, y3, y4, and y2. Okay? And y1, y2, y3, and y4. So, we allow y4 to go in this range in each of these diagrams, and each of them will give us an integral from 0 to 1 with the appropriate vertex operators delta. Okay? So, what are we getting, and it will happen next time before I properly justify this and give you the answer, is that the answer is sum of 6 different different terms, each of which is an integral of this form from 0 to 1. Except that in the 6 different terms, this power is used and s's will get changed. In the different terms, instead of having k1 dot, you see, we have k1 dot k4 here and k2 dot k4 in these two integrals because we were going, y4 was going between 1 and 2. So k1 dot k4 and k2 dot k4. When y4 goes between 2 and 3, this will be replaced by k2 dot k4 and k3 dot k4. Okay? And then we have to write down what each of these is in terms of these SCUs. Okay? So we're going to get 6 different integrals, each of which is the same form, but with different SCUs. Now the other thing to remember is that by the variable change, y4 equals to y4 minus 1, or 1 minus y4, we flip this term and this term. So this is symmetric in the interchange of S and U, or the interchange of 1 and 2. So it doesn't matter what order this is. And it's just given by a choice of U and S. Okay, so the 3 kinematic invariants, S, T, and U. Okay? And we get 6 terms, two of which will have S and U, 2 of which will have S and T, 2 of which will have T and U. And what we have to do is keep it, the thing is to carefully keep track of which diagram gives which dependence so that we keep track of the lambda dependence. Okay? Okay, and it's 2 and 1. It's 2 and 1. So let's make something diagram. Let's write it out. Okay. You see, what is this guy we've already seen is 1 and 4, which is U, and 1 and 2, which is 4 and 2, 4 and 2, which is the same as 1 and 3. Yes, why did I write this was one way. Yeah, this is what it is. Sorry. Okay, U and T. Okay, what about this guy? This guy will give us 2 and 4, which is the same as 1 and 3 plus T, and 2 and 4 and 3, which is the same as 1 and S. This guy will give us 4 and 1, so that's U, and 4 and 1, that's U, and 4 and 3, that's S. Because that's 1 and 2. Okay. This guy is y4, y1, y3. So y4, y1 is U and S. This guy is y4, y2, the same as 1 and 3, so that's T. And y4, y3 is S. Okay, and here y4, y3, which is S, and y4, y1, which is U. Okay, so we've got 2 SUs, 2 TSs. Oh, we've got something. How many SUs? Let's do this again. Y4 and y1, which is U, y4 and y3, which is S. This first, y4 and y3 is S, and y4 and y1, which is U. And this one was,
I think that should be y3.
this is 2 and 3, right? Right, 3 and 2. Sorry. So this one is y1 and y4, which is U, and y4 and y2, which is T. Okay, now we've got 2 SUs, 2 STs. You messed up so badly. So,
1 and 4 is a U.
1 and 4 is a U, yes.
So then that's a U.
This one is a U?
So what is the S?
No.
No.
1 and 4 is a U.
One
UT. UT. Okay, do we have two UTs? UT, UT. We have two STs, ST, ST, and two USSs. Okay, it's probably right. Okay, so now, suppose we write down this answer, whatever this is, as A of, ST. We'll figure out what A and ST is. So this thing is multiplied by what? Trace of, now we look at those that give us ST. So ST and ST. So lambda 1, lambda 2, lambda 4, lambda 3 plus lambda 1, lambda 4, no, what is it? Lambda 3, lambda 4, lambda 2. Just the cyclical ordinance for the two diagrams to give us this. Okay? Plus A of UT. And then the cyclical ordinance for the two diagrams that give us UT. So UT at these two. So we get 1, 4, 2, 3. Plus 1, 3, 2, 4. Plus A of SU, which is 1, 2, 3, 4. Plus SU 1, 4, 3. Okay, we'll continue next time on this one. We probably have to derive it again since actually Portuguese has this wrong. I think this book and it's nice up only indices. Okay, we should just head to almost the document. We'll continue next class. Yeah, there's many things we want to talk about.